Hello, my name is Graham. It is Saturday the 13th of July and I'm going to be talking about the tri-state ant. This is my software, LCEE, which originally stood for the Linux encryption engine, command line encryption engine. And langtons ant was originally designed just to encrypt up data. The very, very first version, which was written in DOS, well, a long time ago, I think it was mid-90s, was done to do compression, because I thought you could compress a ball up of chaos and that you could take core samples of an X and a Y and a Z coordinate with a vector of a certain length. But what I discovered was that there was no way to get past the entropy of a data file that was compressed. So I scrapped it, and for 10 years it sat and did absolutely nothing until one day I had this idea of using it for encryption, because I knew that there was a Gaussian distribution in the data, but it never occurred to me that you could use it for encryption. And when I discovered that langtons ant can be done in a mechanical analog, not only that, but in electronics, and I built a circuit. There is an actual PCB with digital counters on there, very much like the sequencer design for the very original sound cards, and that worked extremely well. Putting the data on that with an oscilloscope and seeing all the langtons ant data coming off from an electronic circuit board was quite weird. So we'll run this. This is the tri-state ant, and how this one works is that instead of having theta as just simply the sum of the lattice, we take the sum of the lattice, which is the trace, and the reason it's round is because there are zeros in there, and they're not quite zero. They're very tiny deltas, and I don't want those in there. What you do is you feed that theta into the Fibonacci function, which you can see here. So rather than ik pi upon 2 theta, which is the normal equation, and we'll just go and remind ourselves of what that looks like. The original one is just simply you have the a coefficient, and you do ik, which is pi upon 4, times the trace, the sum of all the elements in the lattice. What we do with the tri-state ant is we're going to feed that sum, okay, into the Fibonacci function as one of the powers. So it's kind of like a power of a power. It's a very strange thing. And what we find is that the results of this equation will give you which will give you -1, 0, and +1. Those are the only ones. Now, the idea that came from this was that I saw that there was a mathematical way of describing the 3 flavors of the quarks so that they only crossed over an equal number of times. You can't do that with normal Euclidean geometry, because the sine wave will cross over the 0 point twice. So you get four moments where you have -1 and a +1, and then you have 0 twice occurring in that sine wave. And you don't want that for the triplets for the quarks. You want just an equal number of crossovers on the 0 axis as there are -1s and +1s. And that was where this idea of the quarks was born, with the 3 different vectors. So this here and this here, when you're running this equation, is now modeling the quarks as fractional charge and fractional magnetics rather than just fractional charge. And I found that really, really interesting that the Fibonacci was in there. The Fibonacci is not in the electron model, which means that the Fibonacci series in nature, sunflowers and such, that has got to come from the neutrons and the protons in the atom and not from the electric charge. So it's not an electronic property, it is definitely a property of mass. So let's have a look at this further. We still see we're using x, and we're still subtracting 1. But here you can see that we're subtracting the a and the b term separately. So if you take this and subtract it from here, what you'll end up with is a times b plus 1, and then it just becomes real x and imaginary x. The reason I've done it this way was so that by looking at the script, it was very obvious to me which ant was going to be the tri-state or the quad state. The tri-state ANT, I always put -1 in here just so that I know which one it is. We can very quickly go and have a compare of this. So this is just subtracting the b squared term, and we are subtracting the a squared term, where all of this is the 2ab part of the quadratic. And if we go over to the electron one, because obviously the ANT isn't an ANT, it's actually an electron with its electrical properties. Here you can see that we've got a times b plus 1, and we are not subtracting it from here. I hope that's clear. So this is your b squared term, and this is the a squared term, which is psi theta times psi theta conjugate, and we've got the sigma notation multiplied by the e squared. So we've got this and this being multiplied out, which has to be removed. And the other interesting thing about the tri-state ANT is that this bell curve is a lot more obvious. It's still skewed because we're not starting with a lattice that is checkerboard. We're starting with a blank lattice. But it's an interesting, you've got these diagonals. These Langton's ANT here is only changing in 3 distinct directions. And yet we are still seeing a very similar property. It's still Gaussian distributed, same as the quad state ANT. I think we've talked about many other things. The same for this. What I may end up doing is turning this one into the imaginary. So then what we have is we can combine this equation and that equation, modeling the quarks and modeling the electron together as a complete system in one equation. But that's to be done later. I've got other things to be doing right now. So the reason why we're talking about the Fibonacci today is that this will be a precursor to the next video, which will talk about the quarks. Okay. Thank you very much for listening. Bye-bye.